Welcome to my channel once again. In our tutorial today, I shall provide a solution to this very problem. A satellite of mass m orbit the Earth, assuming the Earth of mass m with velocity v at a distance r from the center of the Earth. Derive the relationship between the period t of the orbit and r. So we want to derive a relationship between the period t and the distance between the mass of the Earth and the satellite. That is what we really want to drive here. Okay, so to do that, the first thing, let's consider this should be the Earth. Okay, and then this is the satellite that is orbiting around the Earth. So we assume that if this is the direction the Earth is oscillating, then of course the satellite is also what? Moving in same direction with the Earth. Okay, so we can say this should be the center of the Earth, and this Earth has a mass m. Okay, and the distance between the Earth and the satellite, this should be the distance. Okay, so if this is the distance is given by r, we should name it r. Then if this satellite is orbiting in same direction with the Earth, then we can say this should be the direction, the speed. Okay, v is moving toward that direction. Okay, so if that is true, I want you to understand that if the satellite is orbiting around the Earth on a particular track, if there is nothing holding this very satellite, then it means that there will be a tendency the satellite can fall off the track. Yes, and that will going to take us to the force that is trying to hold the satellite back, not to fall off the track, and that will take us to what we call centripetal force. A centripetal force is that force that try to pull the satellite toward the center of the Earth, so that the satellite should not be able to move away, or as on the process of revolution, the satellite should not move out of the track path. Okay, so centripetal force is actually given by a particular formula. F is equal to mv square all over r, and this is a relationship for centripetal force. We can name this equation 1. All right, then there is also something I want you to understand here. No matter how small this satellite may be, it has its own mass, and that mass is what? Small m. Okay, so this should be the mass of the satellite, while this is the mass of the Earth. Okay, so now there is also something here. There is a certain force between these two masses. Okay, and the two masses are separated by a distance r, and this relationship was established by Sir Isaac Newton, and we call it what? A universal gravitational law. Okay, the man said that the force of attraction between these two masses is directly proportional to the product of the masses and inversely proportional to the square of the distance separating them, and the distance separating them is what? R. So from the Newton law, F is equal to m, or F is equal to g m small m all over capital R square. Now this g is the acceleration due to gravity. This is the constant. Okay, this is a universal constant. All right, so if this is a universal constant, we can also say this should be what? Equation 2. Now from there, we can come over here and say that, okay, equating equation 1 and equation 2, so that we have mv square all over r should be equal to g m all over r square. All right, so one of these m will cancel this m, and r here 1, r here is also 1r, okay, because this is r square. So from here we can have v is equal to g m all over r, and this v is having square. All right, so if that is true, I can name this equation 3. So we will still going to proceed. If the satellite move around and come back to its original point, we said it has completed one cycle, okay, and that is what equal to a period. All right, so if a satellite complete one period, then the speed will be equal to the circumference, because it has completed one cycle. So the speed will be equal to circumference all over the period. Circumference all over the period. And the circumference of a cycle is equal to 2 pi r. Okay? So circumference of a cycle is 2 pi r all over t, which is the period. I can say this should be my equation 4. And if this is equation 3, this is equation 4, I can substitute equation 4 into 3. All right, if I substitute equation 4 into 3, something will definitely going to happen here. All right, so I will have 2 pi r all over t. All of them will have square, because this v is having square. All right, this will be equal to g m all over r. So from here, I'll open up this very bracket so that I should have 4 pi square, then r square all over t square equal to g m all over r. All right, so from here I'll do some little arrangement so that I should have this should multiply this, so I have t square g m equal to this will multiply this. I'll have 4 pi square r raised to power 3, because r multiplied by r square will be r raised to power 3. Okay, so if that is true, I can just say that t square is equal to 4 pi square all over 4m. Okay, all over what? G m, then r cube. All right, so from here t square is directly proportional to r raised to power 3, where 4 pi square all over gm, all of them are constant. And this is the relationship between the period and the what? The distance separating the mass of the earth and the satellite. Okay, and this gives rise to what? The third Kepler's loop. The third Kepler's what? Loop. All right, if you found this very video interesting, make sure you share with your friends.